Color subtraction. The previous lesson focused on the principles of color addition. These principles govern the perceived color resulting from the mixing of different colors of light. Principles of color addition have important applications in color TV, color computer monitors, and on-stage lighting at the theaters. Each of these applications involves the mixing or addition of colors of light to produce the desired appearance. Our understanding of color perception would not have been complete without understanding the principles of color subtraction. In this part of Lesson 2, we will learn how materials that have been permeated by specific pigments will selectively absorb specific frequencies of light in order to produce the desired appearance. We have already learned that materials contain atoms that are capable of selectively absorbing one or more frequencies of light. Consider a shirt made out of a material that is capable of absorbing blue light. Such materials will absorb blue light if the blue light shines upon it and reflect the other frequencies of the visible spectrum. What appearances will such a shirt have if illuminated with white light, and how can we account for its appearance? To answer the question and any other similar questions, we will rely on our understanding of the three primary colors of light, red, green, blue, and the three secondary colors of light, magenta, yellow, and cyan. The process of color subtraction. To begin, consider white light to consist of the three primary colors of light, red, green, blue. If white light is shining on a shirt, then red, green, blue light is shining on the shirt. If the shirt absorbs blue light, then only red and green light will be reflected from the shirt. So while red, green, blue light shine upon the shirt, only red and green light will reflect from it. Red and green light will strike your eye always gives an appearance of yellow. For this reason, the shirt will appear yellow. The discussion illustrates the process of color subtraction. In this process, the ultimate color appearance of an object is determined by beginning with a single color or mixture of colors and identifying which color or colors of light are subtracted from the original set. The process is depicted visually by a diagram at the right. Furthermore, the process is depicted in terms of an equation in the space below. White minus blue equals red plus green plus blue, which is white, minus blue equals red plus green, and red plus green equals yellow. Now, suppose that cyan light is shining on the same shirt, a shirt made of a material that is capable of absorbing blue light. What appearance will such a shirt have if illuminated with cyan light, and how can we account for its appearance? To answer the question, the process of color subtraction will be applied once more. In this situation, we begin with only blue and green primary colors of light. Recall that cyan light consists of blue and green light. From the mixture, we must subtract blue light. After the subtractive process, only green light remains. Thus, the shirt will appear green in the presence of cyan light. Observe the representation of this diagram to the right to the equation below. Cyan minus blue equals cyan is made up of green plus blue minus blue gives us green. For these two examples, we can conclude that the shirt that looks yellow when a white light shines upon it will look green when a cyan light shines upon it. This confuses many students of physics, especially those who still believe that the color of the shirt is the shirt itself. This is the misconception that is targeted earlier in Lesson 2, as we discussed how visible light interacts with matter to produce color. In that part of Lesson 2, it is emphasized that the color of an object does not reside in the object itself. Rather, the color of light that shines upon the object and that ultimately becomes reflected or transmitted to our eyes. Extending this conception of color to the above two scenarios, we would reason that the shirt appears yellow if there is some red and green light shining upon it. Yellow light is a combination of red and green light. A shirt appears yellow if it reflects red and green light to your eyes. In order to reflect red and green light, these two primary colors of light must be present in the incident light. Incident is the light that comes in. Okay. Quick quiz. Test your understanding of these principles of the color subtraction by determining the color appearance of the same shirt if illuminated with other colors of light. Be sure to begin by determining the primary colors of light that are incident, that's what's coming in, upon the object, and then subtracting the absorbed color by the incident colors. Okay, so if we have magenta coming in, absorbs blue. So if we have magenta coming in, magenta is made up of red and blue. So we can say red plus blue minus blue should equal red. Okay. So if we have red and blue is absorbed, well, if we take a look at blue, blue is blue. So we should be able to say red comes in and red leaves. If blue comes in and blue is absorbed, there should be nothing going out, so it should appear black. Let's see how we did. Okay, magenta is red plus blue minus blue equals red. So we got that one right. Red light is a primary color. Blue light would have to be subtracted if present. Since it is not present, there is no need to worry about it. Red light is reflected, so it looks red. And C, blue light is a primary color. If blue light is subtracted, is absorbed, there is no other color left to reflect to our eyes. The shirt appears black because there's nothing reflected. Complementary colors and subtraction. In the above examples, the paper absorbs blue light. Paper that absorbs blue light is permeated by a pigment known as yellow pigment. While most pigments absorb more than a single frequency and are known as compound pigments, it becomes convenient for our discussion to keep it simple by assuming that yellow pigment absorbs a single frequency. A pigment that absorbs a single frequency is known as a pure pigment. The following rule will assist in the understanding of what colors of light are absorbed by which pigment. Pigments absorb light. Pure pigments absorb a single frequency or color of light. The color of light absorbed by a pigment is merely the complementary color of that pigment. Thus, pure blue pigments absorb yellow light, which can be thought of as a combination of red and green light. So blue pigments absorb yellow, pure blue pigments absorb yellow light. So if we take a look at blue, it absorbs yellow, which is going to be the red and the green. So the one across from it is going to be its complementary on what it absorbs. Pure magenta pigments absorbs green light. Magenta absorbs green. Magenta absorbs green and reflects red and blue. Pure red pigments absorb cyan light. Pure red absorbs cyan, which can be thought of as a combination of blue and green. And finally, pure cyan pigments absorb red light. Now, let's combine the process of color subtraction with an understanding of complementary colors to determine the color appearance of various sheets of paper when illuminated by various lights. We will investigate 3 examples. Magenta light shines on a piece of paper containing yellow pigment. Determine the appearance of the paper. Magenta light can be thought of consisting of red and blue light. A yellow pigment is capable of absorbing blue light. Thus, blue is subtracted from the light that shines on the paper. This leaves red light. If the paper reflects the red light, then the paper will look red. So magenta minus blue, and magenta is red plus blue, minus blue will show up red. Okay. And we're not going to be going into that part.